Greetings and welcome to the lecture series System of Equations 4.2 Systems of Linear Equations and 3 Variables. So what does it mean to be a system of linear equations and 3 variables? Well, what that means is it looks something like 2x plus y minus 3z equals 6. So you have 3 variables, x, y, z. They all have coefficients, but there's no powers on the x, y, z, meaning it's linear. In general, we can write it as some constant like a1x plus a2y plus a3z equals a4, where a is just a real number. Any of those a1, a2, a3, a4 are all real numbers. When we're discussing the solution set, we'll start calling it an ordered triple. Triple meaning 3 variables, so we should have 3 solutions. So the solution set for a system of linear equations and 3 variables is an ordered triple. Alright, so let's not mess around, let's just jump in. So let's solve the system. X plus y plus z equals 6, 2x minus y plus z equals 3, and x plus 2y minus 3z equals negative 4. Now the trick of this is going to be, well, we have 3 equations, 3 unknowns. That's a good start. When we had 2 variables, we needed at least 2 equations to where we could solve for the solution set. 3 equations, 3 unknowns, we need 3 equations. We have that. Now what do we do with it? Well, we're going to try and eliminate one of the variables by using 2 of the equations and then using a combination of another 2 equations will eliminate that same variable, and then we'll end up creating 2 new equations from that process. So I said a lot of things, so let's just see it in motion. And for ease, to reference each of these equations, I've numbered them 1, 2, and 3. So if I use equation 1 and I add it to number the second equation, I can eliminate the y, and then I'll create a new equation from that, and I'll just name it 4 for reference. Alright, x plus y plus z equals 6, 2x minus y plus z equals 3. When I add the 2 of them together, I get 3x plus 2y equals 9. That 3x plus 2z equals 9 is going to be my new equation that I've created. And again, I'm just going to call it number 4. Okay. Now that I've used equations 1 and 2, I can use a combination of either 1 and 3 or 2 and 3 to try to eliminate y again and then see what equation I come up with. Okay? So it looks like if I multiply equation number 2 by 2, I'll be able to have negative 2y plus 2y, and the y's will be eliminated. So let's do that. We multiply 2 by equation 2, add it to 3 to eliminate y, and then we'll create a new equation. I'll call it number 5. Alright. 2 times 2 is 4x. 2 times negative y is negative 2y. Z times 2 is 2z, and 3 times 2 is 6. So by manipulating equation 2, I now have 4x minus 2y plus 2z equals 6. And here comes my third equation. X plus 2y minus 3z equals negative 4. That's just the original 3. Add them together, and I'm going to get 5x, no y's, negative z equals 2. That's what I'm going to call number 5. Okay, so let me write down 4 and 5. So here's 4, and 4 was 3x plus 2z equals 9. And our fifth equation that we came up with was 5x minus z equals 2. Now, which is great because I have 2 equations, 2 unknowns, and I got rid of the y, at least for now. So I can solve for either, I can eliminate either x or z, and then I'll only have one variable left to solve for. It looks like 2z and negative z, if I multiply 5, this fifth equation, by 2, I should be able to eliminate z. And then I'll find the value of x in the process. Alright, so the fourth equation is going to remain the same. 3x plus 2z equals 9. 2 times 5x is 10x. 2 times negative z is negative 2z. 2 times 2 is 4. Now I'm going to add the two equations together. 3 times 10 is 13x. The z's will be eliminated. And 9 plus 4 is 13. Well, 13x equals 13. Let's divide each side by 13. So x equals 1. Well, we found one of the variables. So what do we do now? Well, we can plug x, what x is, into either 4 or 5 and solve for z. So let's go ahead and substitute x equals 1 in the fourth equation. Well, 3 times 1 plus 2z equals 9. 3 plus 2z equals 9. Subtract 3 from both sides. 2z equals 6. Divide by 2. Z equals 3. So now that we know what x is, we know what z is, we can use both of those and plug them into any of the three original equations. I'm going to choose 1. So it was x plus y plus z equals 6, so 1 plus y plus 3 equals 6. Y plus 4 equals 6. Subtract 4 from both sides. Therefore, y equals 2. So our ordered triple is 1, 2, 3. A lot of steps, but in essence, we're just kind of eliminating, solving, back substitution, right? A lot of process, long process, and it's very easy to make a mistake in the process, so be very careful and diligent when you're working with linear equations with 3 variables or more. Alright, one's just not enough. You got to see it a couple times to kind of get down what we're going to be doing. So let's solve the system. 2x plus y minus z equals 3. That will be equation number 1. 3x plus 4y plus z equals 6. That will be equation number 2 I'll reference. And 2x minus 3y plus z equals 1. That will be our third equation in our system. It's at this point you want to decide which variable do you first want to eliminate. And since I have a minus z plus z plus z, I think I'll combine 1 and 2 as well as 1 and 3. That way both of those will eliminate z. So the first step, I'm going to use equation 1, add it to equation 2 to eliminate z. I'll create that fourth equation. Then I'll use the same equation 1 and I'll add it to 3 to eliminate that z combination, and I'll create a fifth equation with only the variables x and y. So 4 and 5 will only hold the variables x and y. Kind of have to do a little bit of planning when you're solving this type of system. Alright, so equation 1, 2x plus y minus z equals 3. And equation 2, 3x plus 4y plus z equals 6. Add them together. 2x plus 3x is 5x. Y plus 4y is 5y. Negative z plus z is 0 z's. 3 plus 6 is 9. So our fourth equation is 5x plus 5y equals 9. Alright, let's do 1 and 3 together. 2x plus y minus z equals 3. 2x minus 3y plus z equals 1. Add them together. 2x plus 2x is 4x. Y minus 3y is minus 2y. Minus z plus z is 0 z's. And 3 plus 1 is 4. That will be our fifth equation. 4x minus 2y equals 4. Now that I have two equations, that only consists of x's and y's. We just bring those together. 5x plus 5y equals 9, and 4x minus 2y equals 4. Now I can use any of the methods that I've learned in the past to try and solve a system in two variables. But I'm going to go ahead and stick with the addition method. If I multiply equation 4 by 2, and I multiply equation 5 by 5, I'll get 10y and minus 10y. Therefore, the y's will be eliminated. And ultimately, I'll solve for x as well. So let's do that. All right, 2 times 5x plus 5y minus 9, and 5 times 4y minus 2y equals 4. My result will be 10x plus 10y equals 18, and 20x minus 10y equals 20. Let's add the two equations together. 10x plus 20x is 30x. 10y minus 10y is 0y's. 18 plus 20 is 38. 30x equals 38. So let's divide each side by 30, giving me x equals 38 over 30, but 38 over 30 can be reduced down to 19 over 15. Not, a fun number to work with, but it is just a plain old number. So what if it's a fraction? Now what we're going to do, now that we have a value for x, we're going to plug that back into either equation 4 or 5 to solve for y. Okay? So if I plug it into 4, it's going to be 5 times 19 over 15 plus 5y equals 9. I can reduce a bit. 5 goes into 15 3 times, 5 goes into 5 once. And I'm going to choose to actually eliminate these fractions after all. So right now I have a 3 in the denominator from at least the reduction. So I'm going to go ahead and multiply each term by 3. By doing that, I get 19 plus 15y equals 27. So let's subtract 19 from the right, subtract 19 from the left, and we finally get 15y equals 8, divide each side by 15, so y equals 8/15. Now that we know x is 19/15 and y is 8/15, let's plug those back into any of the 3 original equations. I'm going to go ahead and choose 1, and this will allow us to solve for z, the third and final variable. All right, it was 2x plus y minus z equals 3, so 2 times 19/15 plus 8/15 minus z equals 3. That's 38/15 plus 8/15 minus z equals 3. 38/15 and 8/15 is 46/15 minus z equals 3. I'm going to go ahead and multiply each term to eliminate, that fraction. Multiply everybody by 15. That gives me 46 minus 15z equals 45. Subtract 46 from both sides, leaving me with negative 15z equals negative 1. Last step. Divide by negative 15, divide by negative 15. Therefore, z equals 1/15. So here is our ordered triple. 19/15, 8/15, 1/15. Now, of course, to be on the safe side, maybe you want to plug it all into another one of the 3 original equations and check your solution. But generally, when you get down to this point, you're pretty good. I think probably the hardest part of this whole thing is not necessarily the algebra, but it's planning your attack. Like, what can I do when I have a system like 2x plus 3y minus z equals 5, 4x plus 6y minus 2z equals 10, and x minus 4y plus 3z equals 5? Where do you even start? Well, you have to select one of the variables to eliminate. Sometimes it's easier to eliminate one variable over another. So let's figure this out. If I multiply the first equation by negative 2, that will give me a negative 4x, and in the second equation, I have a 4x, right? So I can eliminate I can eliminate x pretty easily by doing that. But if I eliminate x, I got to stick with that and either combine equation 1 and 3 in some manner or 2 and 3. So let's first do negative 2 times the first equation plus the second equation. All right, so if I multiply negative 2 by 2x plus 3y minus z equals 5, I get 4x. Really? Minus 4x minus 6x and plus z equals negative 10. Had it down here, but I have no idea why I didn't have it the right way the first time. So negative 4x minus 6z plus, because it's, whatever. Sorry about that. Plus 2z equals negative 10. And then using the second equation, 4x plus 6y plus 2z equals 10. I'm going to add these together. Negative 4x plus 4x is 0. Negative 6y plus 6y is 0. Negative 2z plus 2z minus 2z is 0. And negative 10 plus 10 is 0. Well, on the left-hand side I have 0, on the right-hand side I have 0, so guess what? This system is dependent. These are the same line. And therefore, there is no solution to the system. But I want to make it clear that there's no solution to the system, but it's not the null set. Okay? It is literally no solution to the system. Why do I stress that? Because, of course, I have another example. All right? Let's take another system. That's when you come up with something that creates a true system like 0 equals 0 or 2 equals 2. They're dependent. Part of that system are the same exact line, and here's why there's no solution. When you have two equations that are exactly the same thing, they really are. They're just, if you multiply one by, let's say, negative 2 like we did, you get the same line. Then the problem is that you really only have two equations to solve for three variables. There's just no way of doing that. You just don't have enough information. Therefore, no solution to the system. Whereas, if you have a system like x minus 5y plus 4z equals 8, 3x plus y minus 2z equals 7, negative 9x minus 3y plus 6z equals 5. And for argument, let's multiply the second equation by 3 and add it to the third. When we do that, I'm going to multiply the second one by 3, and I'm going to end up getting 9x plus 3y plus 6c equals 21. Third equation is negative 9x minus 3y plus 6c equals 5. Let's add them together. 9x minus 9x is 0. Plus 3y minus 3y is 0. Minus 6c plus 6c is 0. 21 plus 25, or 21 plus 5 is 26. 0 will never get equal 26. Therefore, the system is inconsistent and the solution is the null set. We will never have a solution. Whereas the dependent system, we don't have a solution because we just aren't given enough information to find the solution. So we're going to say at the moment there's no solution. Whereas when 0 equals negative 20, or when 0 equals 26, we know definitely that can never happen. Therefore, it's inconsistent and is the null set. All right, not done yet. Let's work through another system. X plus 3y equals 5. Okay. 6x plus z equals 12. Okay. X minus 2z equals negative 10. Well, all right. We do have three variables, x, y, and z, but not all equations have all of the variables. All right. So I'm still going to number these 1, 2, 3. But I am going to rewrite them just so the x's line up, the y's line up, and the z's line up, so I can kind of figure out what I can combine together to eliminate and get it down to one variable. I still have to get it down to one variable to be able to solve for all three. Okay. If I multiply a negative 1 by the first one and add it to the third one, I can eliminate the x's. I will create a fourth equation. Okay. So that's going to be negative x. Negative 1 times x is negative x. Negative 1 times 3y is negative 3y. And negative 1 times 5 is negative 5. So x, negative x plus x is 0. We eliminated the x. Negative 3y plus nothing is negative 3y. And nothing plus negative 2z is negative 2z. Negative 5 and negative 10 is negative 15. There's our new fourth equation. Right? Even though we kind of seem to have gained y where we didn't have it in the third equation, and we kind of gained a z in the first equation, we still need to do this process. We need to do this to be able to have some way of solving this. Now that I have a fourth equation with y and z, in my original set of equations, I did have one with a y and a z. So why don't we use this second equation and the fourth equation, or actually the fourth equation and the third equation. What did I do here? Yeah, it was actually the second equation. Sorry about that. The fourth equation and the second equation to combine them because they are the equations with the y and z. But I need to manipulate my new fourth equation by multiplying it by 2. So 2 times negative 3y is negative 6y. 2 times negative 2z is negative 4z. And 2 times negative 15 is negative 20. Negative 6y minus 6y is 0. Negative 4z plus z is negative 3z. And negative 30 plus 12 is negative 18. Divide each side by negative 3. Therefore, we solved z is 6. Now, I can plug this into either the fourth equation that we created or one of the original equations that just had either yz or xz. So let's go ahead and plug in z into our third equation. So that would be x minus 2 times 6 equals negative 10. X minus 12 equals negative 10. Add 12 to both sides, so x is 2. Now using x is 2, we can plug it into the first equation, which was x plus 3y equals 5, so 2 plus 3y equals 5. Subtract 2 from both sides, you get 3y equals 3. Divide each side by 3, you get y equals 1. So, x is 2, y is 1, x is 6, so our ordered triple is 2, 1, 6. So, I probably didn't do a really great job on this. It's very hard for me to graph three-dimensionally, but when we're looking at a system and the system has 3 variables, we're really looking at three-dimensional space. Just like a point on a graph is an x value and a y value. So I go over some and up some, or down some. So I have a horizontal movement and I have a vertical movement. Well, now not only do I have a horizontal movement, I have a vertical movement, but I have an outward movement as well. So I have 3 dimensions to work with. And usually when we write that, the x is coming out towards us, y is horizontal, and z is vertical. So if I wanted to plot something like 2, 3, 4, I'd come out towards me 2, go over 3, and up 4, and my point would be floating in space. So since I didn't draw that very well, I do want to show you a picture of what these systems could look like. So let's see if I can work this with the camera. Sorry for the blurriness. So here's our graph, and in essence, if I had 3, 4, 5, I'd come out 3 on the x, move over 4 on the y, and up 5, and I'd be floating in the air, a space in the air, right? Not on a flat plane, but, you know, hovering in the air. When we have these 3 sheets, these planes, when they intersect, at the very point that they intersect, all 3 of them, you have an up and down, side to side, and then the other direction, like the width direction. That point in the very middle, that's what we're solving for. We're looking for where all 3 of those planes cross at the very same time. In a system of 2 variables, we were looking where the lines cross at a very particular point. When we're working in 3 dimensions, we're working with the whole entire plane. Okay? So when we have one singular common point, we'll have a point, an ordered triple as our solution. When they have no points in common because they're all parallel, that's that either, I think I call it dependent, but it's where there's just no points in common. They're parallel. And then another thing is where they're crossing along the whole entire plane, right? They share that plane in common. So that's another case. A fourth case is where 2 of them are parallel and 1 is going through. So perhaps you can find a solution for 2 of the equations, but not all 3, because not all 3 will cross, right? You're looking for the very exact point where they cross. So those are just 3 cases where you might if you plotted these, if you actually graph these, there's really numerous other cases out there, but these are probably the most common that we'll run into. Okay, that's it for this lecture. I just wanted to reiterate that I think the hardest part is not the algebra. The algebra you've been working with for quite a while. It's actually trying to figure out what equations you can combine to be able to eliminate variables. So just practice, kind of play with some of these systems and see what you can kind of come up with. Although I did my combinations like first equation, third equation, first equation, second equation. You could try other combinations to eliminate maybe a different variable first, and those 2 resulting equations eliminating another different variable, and then instead of maybe solving for x, you solved for y, and then you have to plug it back in and do your back substitution. So anyway, that's it for this video. Until next time, be seeing you.